All right, so this is section 1.5, and it's a friendly section, I hope. And the last two sections that we worked on were factoring trinomials. There were 3 terms in every problem. In the next two sections, 1.5 and 1.6, we're factoring binomials, which means there are going to be 2 terms in each problem, and only 2 terms. And when I look at the title, it says factoring sums and differences of squares. So we're focusing on something we call squares. And to be a square problem, you have to only have 2 terms. If you have 1 term, 3 terms, 4 terms, 5 terms, you're not going to be a sum nor a difference of squares. In addition, any letter needs to have an exponent that's a multiple of 2. So the kind of letters I might see like an x squared, or a y to the 4th, or a z to the 6th, or a w to the 8th, or a to the 10th. Those are the kinds of exponents that a letter needs. If I had an x cubed, or a y to the 5th, or a z to the 7th, that's likely not a square problem. And then any number needs to be a perfect square. And to do well in this section, you have to know square roots pretty decently. To be a perfect square, you're something times itself. So I say 1 times 1 is 1, so 1 is a perfect square. 2 times 2 is 4. 4 is a perfect square because it's equal to something times itself. It's equal to 2 squared. And then 3 squared is 9, which makes 9 a perfect square. 4 squared is 16, makes 16 a perfect square. 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64, 9 squared is 81, 10 squared is 100. So those are the kinds of numbers I'm going to see. If I saw a number like 7 or 72, it's likely not going to be a sum or a difference of squares. The big difference between sums and differences of squares are the signs. So I'm going to write examples of sums of squares and examples of difference of squares. So here are just some basic examples of sum of squares. And here are some examples in this next column of differences of squares. So to be a sum of squares, you need a plus sign. I need 2 terms separated by a plus sign. The letters have to have an exponent that's a multiple of 2, and any number has to be a perfect square. So something like this, 9x squared plus 25 would be considered a sum of squares. To be a square, you need 2 terms. The only letter I see is x. It has an exponent that's a multiple of 2. The 2 numbers that I see, 9 and 25, are perfect squares. That makes this a sum of squares. Something like this, 16y to the 4th plus 8 plus, 9z to the 6th. That's also considered a sum of squares because it fits the criteria. There's 2 terms. My letters have exponents that are multiples of 2. My numbers are perfect squares. And it's a sum because it has a plus sign. Something like this, x squared plus 100, would also be a sum of squares. To make something an example of a difference of squares, all I need to do is have 2 terms. The exponents on the letters need to be a multiple of 2, and any numbers have to be a perfect square. So something like x squared minus 81 would be considered a difference of squares because it fits the criteria. There's 2 terms. The letter, its exponent's a multiple of 2. The number is a perfect square. something like this, 49x squared minus 36y to the fourth would classify as a difference of squares because it fits the mode. It has two terms. To be a difference, you need a minus. The numbers I see, 49 and 36, are perfect squares. The letters have exponents that are multiples of 2. And then maybe something like, how about 121x to the fourth minus 4. 121 is a perfect square. It's 11 times 11. And x to the fourth fits the category because its exponent is a multiple of 2, and 4 is a perfect square. So first we need to be able to classify the problems in this section to whether they're a sum of squares or a difference of squares. And once we can classify them, then we can attack the factoring. Turns out that the factoring for both of them aren't that hard. For sums of squares, they don't factor. They're all prime. So when I get into the factoring, every one of these sums of squares do not factor. They are all prime. And I'll kind of help you understand why as I get into the section. Differences of squares all factor. All differences of squares factor. And you get two basically identical parentheses. Except one has a plus sign and the other has a minus. And what goes inside the parentheses are the letters with their exponent divided by 2 and the numbers square rooted with letters with exponents divided by 2 and numbers square rooted. It's maybe a little too theoretical, but when I get done with the section, what I have written here, if you have it in your notes, will probably help you. It shouldn't hurt you anyways. So as I go through the problems in this section, first thing I'm going to do is see if something's a sum of squares or if it's a difference of squares. If it's a sum of squares, I shouldn't even attempt to factor it because it's going to be prime. If it's a difference of squares, it will factor. I'm going to make two parentheses. First is going to have a plus sign. The second is going to have a minus sign. And the rest of what I put in the parentheses is going to be the same. And I fill up the parentheses by doing my firsts and then my lasts. The thing that's written first will go first, except I'll divide its exponent by 2 if it's a letter, square root of it if it's a number. The thing that's written last will go in the last position. And again, if it's a letter, I'll divide its exponent by 2. If it's a number, I'll square root it. Don't know that that's enough, but it's all I want to say right now. I want to get into the problems. And then maybe I'll refer back to this as I think it's necessary. So problem 2 in section 1.5, it fits the criteria to be a difference of squares. It has two terms. There's a minus between the two terms. The only letter I see has an exponent of 2, which is a multiple of 2. The only number I see is 81, and 81 is a perfect square. If you don't know how 81 squares, you just hit the square root button and type 81. The square root of 81 is 9. 9 is going to be part of my factoring. So let me go ahead and factor this. I'm going to make two essentially identical parentheses, except my first one's going to have a plus sign. My second one's going to have a minus sign. And what's going to go first is the thing that was first, but if it's a letter, you divide its exponent by 2. So before I go into my parentheses with my y, I'm going to divide the exponent by 2 and get y to the first power. In my first positions, I'm going to put a couple of y's. Before I put a number in my lasts, I'll look at what's last. If it's a number, I'll square root it. And the square root of 81 is 9. And I'm going to put 9s in the last positions. So I have two essentially identical parentheses. Divided the exponent on the letter by 2. I took the square root of the number. That's my whole answer. And always when I factor, I can check. It's optional, but you certainly can check. To check this, I would FOIL. I'd go firsts are y times y, which is y squared. Outers are y times minus 9, which is minus 9y. Inners are 9 times y, which is positive 9y. Lasts are 9 times negative 9, which is negative 81. And the outers and the inners, because their opposites, are going to cancel. So when I'm simplifying my checking, I'm just going to have the firsts of y squared and the lasts of minus 81. That's all I'm going to have. And that is exactly the original problem, so I know my answer is right. That's all there is to do. So the factoring is really quick. I don't have to do all the extra work that I have to do when I factor trinomials. When I look at problem 4, it's a sum of squares. If they're squares because the exponents are multiple of 2, it's a binomial with 2 terms, the number has a square root. The answer to this is prime. And then let me just down here write the common errors. So it's common for students to say that this factors into y plus 9 squared. It's common for students to say that this factors into y plus 9 times y plus 9. And it's common to say students to say this factors into y plus 9 times y minus 9. All of these are common answers, and they're all wrong. The answer to problem 4 is prime. All sums of squares are prime. If I wanted to show you why each of the common errors is wrong, so these are all wrong answers, the answer is prime. To show you that they're wrong, I'd have to multiply them out and show you it doesn't equal the original one. Y plus 9 squared, if you thought that was the right answer, well, to check it, you'd have to write it as y plus 9 times y plus 9, and then it makes it the same as that answer. And when I FOIL this, the firsts are y times y, the outers are y times 9, the inners are 9 times y, the lasts are 9 times 9, and y plus 9 quantity squared, which is the same as y plus 9 times y plus 9, it FOILs into y squared plus 18y plus 81. Because that's not exactly the same as the original problem, I know y plus 9 squared isn't the right answer. Similarly, this is going to FOIL into the same thing because these are equal to each other, they're just written differently. So that's also going to FOIL into y squared plus 18y plus 81. So that's also not right. This last one, if I FOILed it, to check it, if I thought it was the right answer, I'd go first are y times y, which is y squared. Outers are y times minus 9, which is minus 9y. Inners are 9 times y, which is positive 9y. Lasts are 9 times negative 9, which is negative 81. The outers and the inners are going to cancel, and I'd be left with y squared minus 81. That's not the same as y squared plus 81. It has the same numbers, but the wrong sign. So that makes this wrong because it doesn't multiply to exactly the original problem. Makes these two wrong because they don't multiply to exactly the original problem. There aren't any really other common wrong answers, and anytime I see a sum of squares, meaning it's a binomial, the exponents are multiples of 2, the numbers are perfect squares, I should just write prime and don't do any work. Any work that you might do is going to lead you to a wrong answer. When I look at 6, 6 has a lovely minus sign, so it's a difference of squares. Differences of squares all factor. I get two essentially identical parentheses, one with a plus sign, one with a minus sign. For the b, I'm going to divide its exponent by 2 and get b to the first power. Because b is written first, I'm going to get b to the first power as my firsts. The 49, I need to square root it to figure out what number to put in place of it. So I hit my square root button and type 49. my calculator tells me I'm supposed to put a 7 for my lasts. So because the number was written in the last position, the square root of the number goes in the last position. And again, it's optional, but I certainly can check this. It's not terribly hard to check. To check this, I would FOIL. Firsts are b times b, which is b squared. Outers are b times minus 7, which is minus 7b. Inners are 7 times b, which is plus 7b. Lasts are 7 times minus 7, which is minus 49. The outers and the inners are opposites, so they cancel. I'm going to bring down the b squared and bring down the minus 49 because that's exactly the original problem. I've checked and I know my answer is correct. So differences of squares aren't hard to factor, really. If you can divide exponents by 2 and take square roots of numbers, once you identify something as a difference of squares, it's quick. Sums of squares are easier because they're prime. Next problem, 8, is a sum of squares. It's a square because the exponent's a multiple of 2. The number 49 has an integer square root, and the plus sign makes it a sum of squares. And sums of squares never factor, they're all prime. 10 is a difference of squares because of the lovely minus sign. So I need to take the square root of 16. That's going to be 4. I'm going to divide the exponent of the b by 2 and get b to the first power. And I'm going to square root the 49 and get 7. So I'm going to make 2 parentheses. Other than the signs, the contents are going to be the same. To the left, I need to transform the 16b squared. I do that by square rooting the 16 and getting 4, dividing the exponent of the b by 2 and getting b to the first power. So the 16b squared splits into the firsts, the 49 splits into the lasts. And that's my answer. Again, I could check this, but you certainly don't have to. It's optional, but you can check. To check, you'd FOIL. Firsts are 4b times 4b, which is 16b squared. Outers are 4b times minus 7, which is minus 28b. Inners are 7 times 4b, which is a positive 28b. Lasts are 7 times minus 7, which is minus 49. And always, when I'm checking differences of squares, if I do the full out FOILing, the outers and the inners cancel. You're just left with the firsts and the lasts. And that's equal to the original problem, so I know my answer is quick. So it's a really nice section. Sums of squares, there's no work to do. As long as I can identify something as a sum of squares, it's prime. Differences of squares, it's just a matter of square rooting numbers and dividing exponents by 2. "12 is a sum of squares. It's a square problem because it has 2 terms. 16 has a square root of 4, 49 has a square root of 7, the exponent's a multiple of 2, and sums of squares are all prime. 14 is a difference of squares. So I'm going to get 2 essentially identical parentheses, one with a plus sign, the other with the minus sign. I'm going to square root 81. I know that to be 9. I'm going to divide the exponent of the x by 2 and get x to the first. That's going to make me have a 9x in the first position in each parentheses. And then for the last, I'm going to square root the 25, which is 5. That's going to give me a 5 in the last position of each parentheses, and not really an s. So 9x plus 5 and 9x minus 5 is a perfect answer for problem 14. "16 is a sum of squares again, because 81 has a square root of 9, 49 has a square root of 7, so it fits the squares. It has a plus sign, and this x squared keeps it a square. Sums of squares are all prime. If you look at my little blurb at the beginning, it says any letters have to have x squared, y to the 4th, z to the 6th, w to the 8th, a to the 10th. I look at 20, I see x to the 5th and x cubed. Nowhere in this list do I see x to the 5th and x cubed. So I think, well, maybe this isn't a sum of squares. and maybe it's prime. The thing is, anytime I go to factor, I always have to pull out a common factor, and if a problem has a common factor, it's not considered prime, and that's the case here. I would be wrong to say this is prime because on either side of the plus sign there is an x, so there's a common factor. And when you common factor, if both terms have x, you take the smaller power of x. And now I'm going to take 3 x's away from the first term and be left with an x squared. I'm going to take all 3 x's away from the second term and be left with a 121. So it would be wrong to say this problem is prime because it has a common factor. But it also would be wrong to go any further. Sometimes when I pull out a common factor, I'm left with a difference of squares inside the parentheses that can be broken into 2 parentheses. Here, when I pulled out the common factor, I'm left with a sum of squares. So the answer to this isn't prime, but I can't go further. This is considered the answer. It's not prime because I was able to do one kind of factoring, 1 parentheses common factor factoring, but I couldn't break that into 2 parentheses. And so that's all there is for number 20. If there was a minus sign, if that was x squared minus 121, I'd have to go further and make 2 parentheses out of the x squared minus 121. But it wasn't, so I didn't have to. 22, if I look at the numbers in 22, I see the numbers 2 and I see the numbers 98. Well, 2 is not a perfect square, 98 is not a perfect square. This doesn't look like it's a difference of squares. But just like the last problem, just like the problem after this, there's a common factor. When I pull out the common factor, you'll start to see the square problem pop up. So in problem 22, there's a common factor of a 2. And when I pull out the factor of 2, I'm left with b squared minus 49. It would be wrong to stop here. This is considered partially factored, but not completely factored, because what's left in the parentheses, the b squared minus 49, is a difference of squares, and it can be broken down into b plus 7 and b minus 7. So the best answer for problem 22 would be a 2 as a common factor, and then a b plus 7 and a b minus 7 for the b squared minus 49. Should check this just to show you that I can. To check this, and again, checking is always optional, but it's never a bad idea, I'm going to multiply the 2 into the parentheses that it's next to. I'll go 2 times b and get 2b, 2 times 7 and get plus 14. Done with the 2, now I'm going to go to FOIL. Firsts are 2b times b, which is 2b squared. Outers are 2b times minus 7, which is minus 14b. Inners are 14 times b, which is positive 14b. Lasts are 14 times negative 7. Not feeling that right now, so 14 times negative 7, and I get negative 98 for my lasts. The outers and the inners are opposites, so they cancel. The 2b squared comes down, the minus 98 comes down, and because that's exactly the original problem, I know this thing that I wrote in purple that I said was the answer is correct. 24 is kind of the brother problem of 22, and it's the easier version. There's still a common factor of 2, so it would be wrong to say it's prime. But when I factor out the 2 by dividing the numbers by 2, what's left in the parentheses is a sum of squares, and I can't break a sum of squares into 2 parentheses because sums of squares are prime. So I'm going to say the answer to problem 24 would be 2 times b squared plus 49. The big difference between 22 and 24, in 22 when you factored out the 2 you were left with a difference of squares, which factored more. In 24 when you factored out the 2, inside the parentheses is a sum of squares, and sums of squares are prime, so I stopped there. '26 is written in an odd order because the letter is written second and the number is written first, but I'm just going to leave it in that odd order. And 28 is also in an odd order, but just I'm not going to take the time to rewrite them. If something's given to you in a wrong order, maybe the author wanted it to be in that order, and I'm just going to assume that's the case. Both 26 and 28 are differences of squares. The minus make them factor nicely. So for 26, I'm going to get two essentially identical parentheses, one with a plus sign, one with a minus sign. The 49 comes first. The square root of 49, which is 7, needs to go in the first position. The 16y squared comes second. The square root of 16, which is 4, is going to go in the last position. And I divide the exponent of the y by 2 and get y to the first power, which is also going to go along with the 4. So my lasts are going to be positive and negative 4y. Usually, for differences in sums of squares, I can just write the answer down without showing any work. For 28, the square root of 121 is 11. And the square root of 144 is 12. You can see that. And the exponent is divisible by 2. So this is the difference of squares. So I'm going to get two essentially identical parentheses, one with a plus sign, the other with the minus sign. The first thing I'm going to put comes from the 121. The 121 was first, so its square root goes first. And then the thing I'm going to put second is the combination of the letter and the number that comes from square rooting the 144 and dividing the x's exponent by 2. So 11 plus 12x and 11 minus 12x would be a perfect answer for 28. 30 is a little bit tricky, but not terribly tricky. 32 is very tricky. For 30, I'm going to divide the exponent of the x by 2 and get an x squared. I'm going to square root the 25 and get a 5. And I'm going to make two essentially identical parentheses, one with a plus sign, one with a minus sign. The first are going to be a couple of x squareds. The last are going to be a couple of 5s. And one parenthesis needs a plus sign, the other parenthesis needs a minus sign. I'm done, that's the answer. If this 5 was a number like 9 or 49 or 64 or 100, then I would have had to do more, and I think that's going to come up next. Let me check this to make sure I have the right answer by foiling. First are x squared times x squared. I add the exponents and get x to the 4th. The outers are x squared times minus 5, which is minus 5x squared. The inners are 5 times x squared, which is plus 5x squared. The lasts are 5 times minus 5, which is minus 25. My outers and my inners cancel. I'm going to leave the x to the 4th and the minus 25 and equals the original problem, so I know my answer is correct. 32 is the kind of problem that I probably wouldn't stick on a test, but it's a nice problem to see for homework, and if you take college algebra with somebody other than me, they might sneak this. This is kind of an evil, sneaky factoring problem that a lot of students will get the answer partially right. We'll say they partially factored, but they won't completely factor. So when I do this, I'm going to square root the 81. The square root of 81 is 9. For the x, I'm going to divide its exponent by 2 and get x squared. The 16, I'm going to square root and get 4. And this, I'm going to call this a partial factoring, but not the correct answer. It's right, but it's just not done, what I'm going to write now. And sometimes when you're factoring differences of squares, one of the parentheses is still a difference of squares. So when I look at this, this definitely multiplies to be 81x to the 4th minus 16. It's factored correctly. But when I look inside the parentheses, the first parentheses is a sum of squares. It can't be factored again. The second parentheses is a difference of squares, and this one needs to be broken down into two parentheses. So for the complete factoring, the best answer, again, I wouldn't ask for one of these on a test, but there are certainly teachers that do, and it's nice to be able to know their tricks. What I'm going to do is I'm going to break this 9x squared minus 4 into two parentheses, one with a plus, one with a minus sign. I'm going to square root the 9 and get 3. I'm going to divide the exponent of the x by 2 and get x to the 1st. I'm going to square root the 4 and get 2. So 9x squared minus 4 factors into 3x plus 2 times 3x minus 2. That's the final answer, and it's considered completely factored. The answer above it is correct, but like I said, it's just partially factored because one of the parentheses is still a difference of squares. It should be factored more. If you catch it, it's good. If you don't catch it, to me, it's not such a big deal. But it's a trick that comes up in every intermediate algebra book. 34 is a mess. It's got to be a common factor. 50 is divisible by 2. 128 is divisible by 2. I'm going to factor out a 2. 50 divided by 2 is 25. So I'm inside the parentheses. I'm going to have a 25 and x to the 4th. 128 divided by 2 is 64. I'm going to have a 64 and a y squared. So the 2 is going to be part of my answer, but it's not going to change on this next step. On the next step, I'm going to leave the 2, and I'm going to make 2 parentheses, one with a plus sign, one with a minus sign. For the firsts, I'm going to square root the 25 to get a 5. I'm going to divide the exponent on the x by 2 and get an x squared. So I'm going to write 5x squared in for my firsts. And for my lasts, I'm going to square root the 64 and get 8. I'm going to divide the exponent on the y by 2 and get y to the first. So I'm going to go 8y and 8y. This is going to be my answer, and I can't go further with this. The reason I can't go further is because neither of these are differences neither one of these are differences of squares. This one's a plus, it had no chance. This one, the 5 doesn't have a nice square root, 8's not a perfect square, the exponent on the y isn't a multiple of 2. So this second parenthesis is not a difference of squares. It would have to be like 25x squared minus 81y to the 4th or something. The numbers in this parentheses would have to be perfect squares, and both the exponents would have to be a multiple of 2. So I can't go further on this like I could the last problem. (36), it's a difference of squares. I'm going to divide the exponent of the y by 2 and get a y squared. I'm going to square root the 81 and get a 9. So this is going to factor into y squared plus 9. That has absolutely guaranteed to be prime because it's a sum with squares. The second parenthesis is y squared minus 9. You have to look at both parentheses after you factor with a square and see if you're left with another square, a difference of squares at that. And this parentheses has a difference of squares stuck in it because the exponent's a multiple of 2, there's a minus, and the number has a square root. So again, this is considered partially factored. It's not a wrong answer, but it's not done. To completely factor this and get the correct answer, I'm going to break this down by square rooting the y squared, by dividing the exponent of the y by 2 and getting y to the first, and square rooting the 9 and getting 3. So the completely factored answer, the first parenthesis is a sum of squares, it's prime. The second parenthesis is another difference of squares, so I can make it into 2 essentially identical parentheses, one with a plus, one with a minus sign. So again, I can't ever imagine putting something this tricky on a test. We've done a couple of them, but that's just not really something I feel important enough to put it on a test. Numbers are out of control in 38. I'm going to have to use my calculator for certain. So for 38, both 2 and 1250 are even, so they're divisible by 2. I'm going to factor out a 2. It's going to leave me with an x to the 4th, and then I'm going to go 1250 divided by 2 and be wound up with a 625 inside my parentheses. I think I'm going to be able to make this into 2 essentially identical parentheses, one with a plus, one with a minus sign. For the x to the 4th, I'll divide its exponent by 2 and get a couple of x squareds. And the 625, I need to square root the 625, so I hit my square root key. I'm typing the number 625, and the square root of 625 is 25. So after my signs, after the plus and the minus sign, you should get 25s. Just like the last problem, this is only considered partially factored, so I got a little bit crazy with these. The first parentheses is a sum of squares, it's prime. The second parentheses is a difference of squares. So for the x, I can divide its exponent by 2. For the 25, I could square root it. And for the final answer, I can write a 2, an x squared plus 25, and an x plus 5x minus 5. So anytime you factor, especially when you start with an exponent of 4, there's a chance that one of the parentheses is another difference of squares, and differences of squares all factor, and so you should factor them if you see a difference of squares. Getting close to the end of this already. Numbers are insane for number 40. I'm going to have to break out my calculator because I have no idea what the square root of 4096 is. 42 is going to be easy. You might jot down an answer to 42 before I get there. So for 40, I think it's a difference of squares. I'm going to divide the exponent of the y by 2. No idea what the square root of 4096 is. So I use my calculator to do the square root of 4096. I just hit the square root button, which is right next to the x squared key, between the fraction key and the x squared key. And the square root of 4096, of course, is 64. So I'm going to make two essentially identical parentheses, one with a plus sign, the other with a minus sign. The first parentheses is a sum of squares. It doesn't factor anymore. The second parentheses is a difference of squares, so I should factor it. I'm going to divide the exponent of the y by 2. I'm going to square root the number. And for my final answer, I'm going to leave the first parentheses, y squared plus 64. And the second parentheses, I'm going to make a y plus and a y minus 8. Last problem is a sum of squares, and sums of squares are all prime. That's the whole section. I just wanted to pop up the stuff that I wrote at the beginning. I don't know that this makes more sense now or less sense now, but I said sums of squares do not factor. They are all prime, and we're consistent with that through the semester, this whole section. Differences of squares, you get two essentially identical parentheses, one with a plus sign, one with a minus sign. The letters, you divide their exponents by 2, and the numbers we square rooted. So that's the heart of this section. So when you have binomials, if the letters have exponents that are multiples of 2, and the numbers are perfect squares, that puts you into a square problem. There's squares with minuses that do factor, squares with pluses that don't factor. And we fact squares with pluses, we stop and we write prime. Squares with minuses, we get one parentheses with a plus, one parentheses with a minus. Any exponent on the letter we divide by 2. Any number we take the square root. And then we should take the time to make sure what's left in my parentheses with the minus sign doesn't factor more. So that's the whole section. The next section's binomials again. It's binomials that are cubes. And it's also kind of friendly. And we'll just get to that when we get to it.